So I state a lemma called Gursa's lemmas. So here for rings, you know, Gursa was a student of Hermite. He was supposed to generalize the classification of Frobenius of finite subgroups of O3 to O4. And actually, O4 looks a little bit like O3. And so he had a lemma, which is the key for his thesis, which is here for rings, but it's for anything, basically. You have 3 rings and 2 homomorphisms. And you assume that they induce an injection, so they are surjective. And you assume that they induce an injection to the Cartesian product of the rings. So you have this situation, and you consider an ideal of, so 2 ideals of T. Here, C1 is the kernel of theta 2, and C2 is the kernel of theta 1. So they are ideals in T. And so they have a special property, namely that if you restrict theta 1 to C1, it is an isomorphism to something which I denote by eta pi 1, which is an ideal in T1. Because, you know, the second projection is 0 by assumption. C1 has second projection 0. And so the restriction of theta 1 to C1 is an isomorphism to its image. And similarly, the restriction of theta 2 to C2 is an isomorphism to its image in T2. And the lemma of Gursa tells you that if you consider the sum of C1 and C2, then the quotient T over C is isomorphic to T1 over eta 1. Eta T1, maybe, sorry, eta T1, or maybe, eta T1, eta T2. So this is the map theta 1 bar, okay, modulo, this is theta 1 modulo what? And you have theta 2 bar going to T2 modulo eta T2. You have these isomorphisms. So the fancy formulation is that the image of this in the product of these 2 rings is the graph of an isomorphism of these 2 rings. So this is the lemma of Gursa. Well, if you want, it's just the composite of these 2. And so this is an exercise of undergraduate level, which is a nice exercise. Do I prove it or no? Maybe not. Okay, it's an exercise case. Very easy once you have the statement. Okay, so this is Gursa's lemma. So we apply it to T will be the Hecke algebra modulo torsion, which is an O algebra. Of course, if the rings are O algebras, we have isomorphism of O algebras. So T will be this. We will consider theta pi, the Hecke eigensystem associated to our cuspidal automorphic representation. So this is T1, and we have another thing, T prime. I remind you that T tensor E, or T bar tensor E, is semi-simple. So this splits into E times another algebra, T prime. And I define this T prime as the image. So of course, this is subjective, as the image of the integral thing T bar in this by the second projection. So we have this picture, and then, well, you have this quotient, okay, which is isomorphic to that quotient by Gursa's lemma. And so that's the definition. Also, this object is called the Hecke congruence module, but it's a ring, actually, as you can see. But it's denoted C0 of theta pi, This is O modulo eta pi. This is the Hecke congruence module, which is a ring. And eta pi is the congruence, well, ideal, but number. Okay. Congruence number, it's an ideal. Well, it's an ideal in O. And as I said, another definition, which I leave as exercise maybe. So you have two idempotents in this algebra, but they are not here. This is a local ring, okay? This local ring has no idempotents as a local ring, but this is not a local ring and it has idempotent. So 1, 0, which I denote by 1 pi here, and 1 t prime, which is 0, 1. Okay, so you have these two idempotents here, and as I said, so as you can see, this is the unit of this component. So you can view, well, so theta pi is nothing but the endomorphism of multiplication by 1 pi, which is actually a map from T, from TE to E, okay? And which sends T to O. And it's an easy exercise to show that eta pi is the denominator of 1 pi relatively to this integral structure. So that's another definition of the congruence number. Don't do it. An exercise. Very easy, okay? Okay. So that's the definition of the Hecke congruence number. And again, there is M congruence number and M congruence module. So you take M to be a finite flat O module with action of T. So, it will be T, it will be the Hecke algebra modulo torsion, but yeah, let's write T. And so we have this decomposition TE equal E times T prime E. We have the idempotents, 1 pi and 1 T prime. And we have the module M. We tensor the module by E. Then we have the decomposition 1 pi ME plus 1 T prime ME. And so M has an image here, which I denote by M pi. So if you want, so as I said last time, M upper pi is the image of M by 1 pi. It's a O module, O submodule of this, which is supposed to be one-dimensional. Okay, as I said, this is the assumption I make. This is supposed to be one-dimensional. So this is an O submodule here, but it is not contained in M because this map is not all right. So, but on the other hand, you have M lower pi, which is M intersection with 1 pi ME, which is of course a sub of M, and obviously it is a sub of M upper pi. And then you consider the quotient M upper pi modulo M lower pi. So this is called the M congruence module. And as we said, it is isomorphic to O modulo something, which is called the M congruence number. And it may not be equal to the Hecke congruence number, but it is always a divisor. You always have that eta pi of M divides eta pi, and equality holds if M is free. If M is free over the Hecke algebra. modulo torsion, which I don't assume and which sometimes is not proven, okay, which was not true, depends on M. Okay, so that's the congruence numbers. Then there is the notion. So now we will relate those to L values, adjoint L values. So this morning, Raghuram introduced the notion of critical values. And so I recall the definition. So if you have a motive over anything, but let's say over Q, you consider the Archimedean component of the motive and Archimedean component of the dual twisted by, well, 1 minus S. So they are product of gamma factors. So if this function have no pole at S equal N, both of them, then N is called critical for N, for the motive. So here, let's consider a classical modular form of some level gamma 1n, maybe new form. And so it corresponds to a cuspidal automorphic representation on a GL2 of the adels. But actually, it is, well, in that particular case, it is proven that there is a motive, MF, of rank 2 over Q with coefficients in some number field, which is called the Hecke. The best number field you can take is the Hecke number field, the field generated by the Hecke eigenvalues. But we can take a bigger one, so some number field. And so it has Hodge-Tate weights, Hodge weights, if you like. So if you take the Durham realization, it decomposes as M k minus 1, 0, plus M 0 k minus 1 over C. So it has weight k minus 1 and 0. But if we consider the add 0, okay, add MF, this is a weight 0. This is a motive of weight 0 and pure. And it has Hodge-Tate weights. So this number I call the weight. So this is pure of weight W. Pure of weight W. Here, but this one is weight 0, and if you call it N, so the decomposition is NW minus W plus N00 plus N minus W. So the Hodge weights are W, 0, and minus W. And so using that, because you need the Hodge weights to determine the criticality, and so using that, you can find the critical values for these motives, and you find the following. You find the integers between minus W and 0, which are even, and the integers between 0 and W, which are odd. So these are the critical values. So in particular, 0 is critical and 1 is critical. And we are especially interested in this value, which is critical. And the theorem of Hida is that if you divide this by the Manin periods, you take the product of the two Manin periods. Well, of course, you have to complete by the Euler factors at infinity, which are these L infinity. Well, this is equal to eta pi. Actually, this is equal to eta pi of some module, namely the H1 of the modular curve with coefficient in Vn of O. So that should be this, this module, but it turns out that by the work of, well, it starts with IISER and Wiles, this is free over, or maybe you put a plus minus. I will explain. This is free over the Hecke algebra. So actually, this M congruence number happens to be the Hecke congruence number because this module is free over Hecke. So this is the theorem of Hida plus IISER, Wiles, saying that this is free of rank 1 over, well, of course, when I say that, it's up to unit, up to O cross. O is the ring, is the, let's say, valuation ring at some place dividing P inside the Hecke field E. So this is a perfect substitute of the Bloch-Kato period because, okay, assuming some Taylor-Wiles assumptions, this is exactly the cardinality of Selmer, which I mentioned, but we don't need that. But I just tell you that this is a perfect substitute. This I should call omega pi automorphic. This is my definition. I never defined really what are the automorphic periods. So here, this is the automorphic period, and it happens to deserve the name Bloch-Kato period, although it is defined in an automorphic way, and this is defined in a motivic way, but it should satisfy this, and this one satisfies what you want, namely that this is Selmer Q adjoint rho F, rho pi, tensor E over O, which is a finite group. This is proven, and so this formula is proven. Well, I would say I assume that P does not divide N. Well, okay, maybe P does not divide 6 times N, phi of N. It's kind of, this is the Euler function. In the theorem of Hida, you may have this assumption, and maybe also P greater than K. Yeah, you have all these assumptions. But you see, if you look at tables of congruences for a cusp form, usually the congruence occur for very large primes. So these primes are kind of trivial, that we are excluding some small non-interesting primes, and still this number, so you take P to be very large, maybe 5 or 6 digits, and this is the kind of number we find as congruence primes. So this is still interesting, even if you remove these primes. No, omega pi automorphic is defined now. This is my definition of omega pi automorphic. Omega pi Bloch-Kato is a number defined by Bloch-Kato such that the L function of this motif divided by this period is cardinality of Selmer of this motif. Oh, yeah, you're perfectly right. Yeah, you're right. This is the motif ad rho pi. Yeah, this is N. This is the N. Yeah, of course. Yeah, you're right. Here it's really pi. Yeah, true. Yeah, we are dealing only with this kind of adjoint motifs everywhere. So, okay. So this is the first theorem. Now we want to state more theorems of this type. As I said, it is some work, of course, but it's not so hard. They all follow the same line of proof, which is to relate the adjoint L value to a Peterson product, Peterson norm. And this Peterson norm, I will explain how it is naturally computed as a congruence number. This is part of the formalism of the congruence number. So, but the fact that L, adjoint L can be computed as a Peterson product is some analytic fact, which is not always proven. Okay. So the next, yeah, so we have to be a little careful about this type of adjoint L. So we consider pi on GLN of AF. F is a number field. And actually, if n equal 2, so if F is totally real, okay, so n equal to F totally real, we will have 1 is critical for adjoint rho pi. But otherwise, if n is equal to 2 and F is not totally real, or if n is strictly bigger than 2 and F is anything, this is not critical. Okay? If n equal to F not totally real, or n bigger than 2, 1 is not critical. And our method does not care about criticality. It works as well in these cases, although it's not critical. But... So I remind the theorem. I remind you the theorem of Dimitrov. So this is 2005. So you take GL2 of totally real. So you take pi, cuspidal, cohomological, and you take add rho pi at 1. You have the periods which I called omega pi epsilon and omega pi minus epsilon. So epsilon is a character of the group O2 of F infinity modulo SO2 of F infinity, which is plus minus 1 to the power IF, the set of embeddings of F into Q bar. So when you have this character, you can define this period. So of course, minus epsilon is not the opposite of the character, because the opposite of a character is not a character. It is another character which is defined. You have this basis, and you have, let's say, epsilon, and you consider epsilon of the basis. So E sigma for all sigmas. Epsilon of E sigma is something. Well, you define minus epsilon on the basis by minus epsilon of E sigma. Okay. It's another character which has the property that on the basis it is given by these values. It's not, okay. It took me some time to understand that minus epsilon is not the opposite of epsilon. Okay, so, and this deserves, again, the name of omega add pi automorphic. And the theorem of Dimitrov is that this is eta pi of HD of the Hilbert variety with coefficients in Vn of O. And again, under Taylor-Wiles assumptions, this, when you localize, because, yeah, you see, we are talking about congruences. So if you localize at a maximal ideal associated to pi, does not change the congruence ideal, okay? Because you don't have congruences between this localization and another localization by definition. So you can localize. And it turns out that under mild assumptions, this is free over the Hecke algebra. So actually, this is also eta pi Hecke, the Hecke congruence number. So under Taylor-Wiles assumptions, maybe, which are anyway necessary in many things later. So you need to know whether this is free or not. The truth is that you have this theorem, and now if you know that this is free, so that's Dimitrov. You have to assume that rho pi bar is absolutely reducible. And yeah, maybe you'd, yeah, under this assumption, you even don't need that. You will need that in order to say that this is equal to cardinality of Selmer. Yeah, okay. Okay, so I'm sorry. So this is okay, and this, yeah, until here, you don't need Taylor-Wise. You need this irreducibility plus P greater than K, and P does not divide 6 norm of Gothic n, phi of Gothic n, where n is the level. You will assume that the level is U0 of Gothic n. Like that. So you have this theorem of Dimitrov. Then, so we are still in the critical case here. I said it, yeah. So here, this is a critical value. But now if we take an imaginary quadratic field, so now we take pi cuspidal cohomological on GL2 of an imaginary quadratic field, F imaginary quadratic. So you remember that in that case, you have two interesting cohomology groups, H1 and H2. Okay, bottom is 1, top is 2, and L0 is 1. And so you have two periods, omega pi 1 and omega pi 2, which were defined. And so you have the theorem of Eric Urban. This is his thesis, 1995. So lambda of adjoint rho pi 1, this is not critical, divided by omega pi 1, omega pi 2. So you see it's a new type of automorphic period. This is the automorphic period for the adjoint. Is eta pi of a cohomology module. So I will say H1 or H2, and I will explain that. It can be any of them, H1 of Y, Vn of O, or also H2, because they are duals and the congruence number is invariant by duality. They are dual by Poincaré duality. Because this is diagonal, okay? So it is self-dual. This is actually NN. NN. The weight is NN. Okay, and there are some assumptions called which are satisfied in that case. Again, under some sort of Taylor-Wiles assumptions, this is eta pi, the Hecke congruence number. But well, what you prove is this. Okay, so this time it is not critical, but still people were happy with this theorem of Eric Urban because it was a new phenomenon. Okay, so just see that I don't forget. Critical, Dimitrov, yeah. Yeah, and there is another case which is under investigation by my student Zheng Wang, but it must work because the relation between adjoint L and the Peterson product has been established by very difficult works of Bezard-Plessis, Chaudoir, and Morimoto. But so it is the case of the group, so pi cuspidal automorphic on U21. Here, it is critical. This is a critical value. And here, the periods, I can tell you, in my first talk, I defined for a classical modular form, I defined omega coherent 1, or omega 1 coherent. You remember? Using coherent cohomology. So here, for the Picard variety, which is a surface, you have H0, H1, H2, 3, H4, just a second. We will deal with coherent cohomology. The periods are coherent cohomology periods. I may come back to that. Okay. The product of 2 omega pi, but middle degree is 2. Middle degree is 2, omega 2. There is only one thing. Yeah, okay, I'm sorry. Okay, well, you can define omega add rho pi automorphic. I will come back to that. And you should prove that this is eta pi of H2 of the Picard modular surface. So this is a work in progress, but the main step, which is the relation between this and the Peterson product of some automorphic form on U21 has been proven. So this is proven by Bezard-Plessis, Chaudoir, and Morimoto. So you should have. And again, this is a situation where under Taylor-Wiles assumptions, you have equality with eta pi. And by the way, you have equality with cardinality of Selmer under Taylor-Wiles assumption. Yeah, okay. Well, okay, so here, yeah, okay, this is correct. This is correct. But here I don't say, and this is absolutely false, that this is cardinality of Selmer in the case of Urban, okay? In the case of Urban, there is a nice, there is a relation, but this relation is given by a number which is called the Wiles defect. So this is not the cardinality of Selmer, but this can be explained. In that case, the difference is some interesting number, which has a commutative algebra definition, and it is called, so the quotient, so I don't remember, but the quotient is the Wiles defect. In that case, it's not equal. Maybe at the last talk, I will define the Wiles defect. Okay, so this I keep. So these are the starting point of our work. And so, okay, and there is, of course, there is a last case where there is unfortunately a small defect of the formula, which is the theorem of Balasubramanyam and Raghuram. Again, this is part of the starting point. We need all these theorems to start. Balasubramanyam and Raghuram. This is more general. You take a GLN over F. So for us, F is either totally real or CM for simplicity. Then you have a theorem that lambda adjoint rho pi 1. So as I said, if n is greater than 2, this is never critical. So here the periods will be omega pi bottom epsilon in case totally real, and omega pi top minus epsilon. And that should deserve the name of omega automorphic add rho pi. But there is a factor here, C infinity equal eta pi. And this factor is conjectured to be a p-adic unit. Conjecturally, and we can prove that with Baskar for GL3 since few days, thanks to the artificial intelligence. It's an awful calculation. So that's the problem. We know the calculation to do, but we cannot do it. Okay? There is a the problem of calculating awful integrals. So, so for GL3 of imaginary quadratic, which is the case we are interested in for our work, GL3 of F imaginary quadratic, this is okay. Okay. Of course, in that case, there is no epsilon. Doesn't change much. Okay. So all these theorems are our starting point. So now, before explaining the results, we will have to do some algebra. Hope you like algebra. We will do the formalism of congruence numbers, because some properties are crucial for formulation of the results. So again, we have a DVR, we have the field of fractions, and we have T finite flat over O. And we have, okay, I changed the notations. Now it's called lambda. So we have an O algebra homomorphism, lambda. You see the theta pi, but we changed the name. Okay. And we assume that when you tensor by E, this splits. So it becomes E times T prime E. Okay, and so we have the congruence. We have the congruence, well, anyway. So, and we have a module, M. M is so we have 1 pi and 1 T prime. So M is a finite flat O module with action of T. And we assume that 1 lambda M is ME is dimension 1. Okay. We could work with higher dimension using fitting ideals, but well, in our situation, we will manage to get this one dimensionality. So the first result is the duality statement. We assume we have a perfect pairing. So duality. So we assume we have a perfect pairing, M times N with values in O, perfect, and which is bilinear, which means that Txy equal Xty for any T in T. Then this pairing induces a perfect pairing Pontryagin duality between C0 of M lambda and C0 of N lambda with values in E over O. So corollary, eta lambda of M is equal to eta lambda of N. We'll have the same cardinality. So I sketched the proof. This is a pure algebra. So ID. So if we have a perfect pairing V times V prime to E, perfect E bilinear pairing, and we have lattices lambda 1 inside L1 inside V O lattices, 2 O lattices. And we consider the dual lattices, so which means that we consider lambda 1 prime, the set of vectors V prime in V prime, such that V prime L1 is contained in O. And similar, lambda 1, sorry, lambda 1, and similarly L1 prime the vectors V prime in V, such that V prime L1 is contained in O. Of course, the inclusion now is reversed. L prime is contained in lambda prime. And we know, this is well known, that we have a perfect Pontryagin duality between this and that, induced by, so induces perfect, sorry, E over O, a perfect Pontryagin duality like this. Okay, so now we apply this easy thing to, so for us, we will consider VE to be, so just a second, to be ME. And well, actually, it's even more trivial for us. It will be 1 lambda ME, and V prime E will be 1 lambda NE. So what is the first lattice? Lambda 1 will be M lambda, and L1 will be M lambda. So we know that this is contained in this. This is a one-dimensional pairing. So we are doing very trivial things. This is one-dimensional, I remind you. Maybe I give this stupid proof because you see the phenomenon of denominators, and we are working with a one-dimensional vector space. Okay, so it shouldn't be too hard. So we have to prove. You see, what we want is a duality between M lambda over N M lambda and N lambda modulo N lambda modulo N lambda. We want to have this perfect duality. So we apply the lemma, and so we have to prove something quite clear, which is that M lambda prime is N lambda, and M lambda prime is N lambda. That's what we have to prove to apply the lemma. So we prove only one of them. So let's prove one inclusion. So first of all, we prove that N lambda is contained in M lambda prime. So what does it mean? It means that if you take something here and you pair it with something in M lambda, you get an integer. So you take N in N lambda, and you take something which is 1 lambda M inside M lambda, and you pair them N, comma, 1 lambda M. So what do you get if you do that? Well, I remind you that this is Hecke linear, so you can move the 1 lambda. And if you move the 1 lambda, nothing happens because this is fixed by 1 lambda. So this is N. So we have two things which are integral. So this is integral, and that's it. So this is one inclusion. So the other inclusion is slightly more interesting. M lambda prime is contained in N lambda. So we take an element in what? Y in, I take an element in 1 lambda NE. Okay, in the vector space generated by this. And I assume that when you pair it with M lambda, it is always integral. In other words, I take an element here, okay? Because we know that this is contained in N this is contained in 1 lambda NE. Okay? This is contained in 1 lambda NE. So I take an element of 1 lambda NE, and I assume that when you pair it with m lambda, it's an integer. So this means that if you pair it with 1 lambda x, it is an integer, where x is in m, but you can move that. You get 1 lambda y, x, and this is y, okay? Because we are in 1 lambda, this is an idempotent, okay? So this is yx, and this is an integer. This means that y paired to any element of m is an integer. So this means that y belongs to n by perfect duality. So it belongs to n intersection 1 lambda ne, and that's by definition n lambda. And that's it. Okay, here we have something which pairs with any element in M as an integer, so it is integral. And so it belongs to this. All right, so, well, okay, that's the proof. But the corollary, which is the key of this thing, this is the famous calculation of the congruence number as a pairing, so corollary. If we denote m lambda, if we take a basis of m lambda O delta 1, and we take a basis of n lambda O delta 2, then if you pair delta 1 and delta 2, what do you get? You get the congruence number eta pi of m, of m or of n, because we just proved this is the same, okay? And so that's the key. So why is it true? Well, because we have just seen that there is a perfect duality between m lambda and n upper lambda. This is perfect. Okay? But, so if we take a basis of this one and a basis of that one, we get 1. We can get 1. But here we take delta 2 to be in n lower lambda. So how can you compute delta 2? We can compute it as, by definition, as eta lambda, okay, it's a lambda, eta lambda of, you see, delta 2 is eta lambda of n times a basis E2 basis of n upper lambda. And we know that delta 1 E2 is 1. So, of course, delta 1, delta 2 is eta lambda of n, or eta lambda of m. Okay, because this is 1, but this is this vector times this constant by definition of this constant. So you see that you can compute this cohomological congruence number as a pairing between m lambda and n lower lambda. So if you pair this thing, this is the ideal eta lambda of m. So this is the key formula, which will be used using Poincaré duality, which can be related to Peterson product, to compute, so adjoint L is Peterson product. Peterson product can be interpreted as Poincaré duality, and Poincaré duality gives you this, provided you take bases of these modules. And how do you get bases of this module if you remember the definition of the periods? Well, you apply Eichler-Shimura to some nice automorphic form, and you divide this nice automorphic form by the corresponding period, so that this becomes a basis of m lambda. So basically, you will have, let's say, iota top and iota bottom of phi divided by omega bottom. You take the Poincaré pairing of these two things, and you get this number. You put this out, this is Peterson, and Peterson is adjoint L, and that's it. Okay? So this comes from, this is the definition. The period is defined so that Eichler-Shimura of a well-chosen automorphic form divided by the period is a basis of this M lambda. That was the definition of the period, okay? So you will have basis of these modules. And so the formulas are proven from this, okay? Essentially. Okay? You have to relate Poincaré and Peterson, but that's standard. It's some work, but... Okay, so there are more formalism. Yeah, now we will introduce base change. So for the moment, we introduce it formally in terms of algebra, in terms of Hecke algebra homomorphisms. For the moment, you see, there was no base change at all. There was only one group G. Now we will have two groups. So we introduce, but for the moment, I am formal. So I consider the situation of two finite flat O algebras plus one homomorphism of O algebras. Okay? And I assume that theta is surjective. So TIs are finite flat O algebras. So this is the so-called base change homomorphism between Hecke algebras. It will be. But for the moment, just abstract. And we consider the composition, lambda 2. And so we define relative congruence numbers for Hecke and for cohomological modules. So for Hecke, the situation is as follows. So we assume, of course, that T2E splits. So splits, so that theta splits. So you can write it as T1E times something, which I call maybe T double prime to E. And the first one also splits as usual. T1E is E times T prime E. So this is the situation we considered earlier. And that's the new situation. We assume this splits also over E. So the first projection here is theta E. Here, the first projection is lambda E, lambda 1 E. Okay. We split this and we split that. So actually, we could also split T2E as E times T prime E times T double prime E. So here, that would be something which I maybe the first projection here would be lambda 2 E, because lambda 2 by definition is lambda 1 composed with theta. So we have all these splittings, but these two are enough. This is automatic. Okay? So we have these splittings, and we introduce an ideal, which is something maybe C2 over 1, which is the kernel of theta T double prime. Okay, you have T2, which is in here. It has projections. The first projection is T1, and there is another projection, and the image is called T double prime 2. So this first map is theta, and this second map is maybe theta T double prime 2. Okay, so just as before, you consider this as an ideal of T2, and as you see, this is actually, you can apply theta, and so theta is an isomorphism between this and some ideal of T1. Its image, I don't know, for the moment it's just the same. And therefore, you can apply lambda 1. And that's the definition of That's the definition of the relative congruence number. That's the notation, eta lambda sharp. Okay, so that's the relative congruence, the Hecke, so relative Hecke congruence number. And I can tell you what it is good for. It is good for creating congruences between something which is a base change and something which is not a base change. We say that lambda 2 is the base change of lambda 1. But you see, the situation is as follows. We can apply again Gursa lemma for the following diagram. T2 goes to T1 by theta, and T2 goes to T double prime 2 by theta T double prime 2. And what is the meaning of these morphisms? So when you have something, when you have a morphism to O, from T2 to O, either it factors through theta, and we call it a base change, or it factors through theta T double prime 2, and we call it a non-base change. And the relative congruence number is something which relates base changes and non-base changes. And so here, so this is a little big, but now we consider one specific map, lambda 2. And the question is, which is a base change, okay? Because it is given by, so this lambda 2 comes from lambda 1, actually. Okay? Lambda 2 comes from lambda 1. And the question is whether it is congruent to something here. And the answer is that lambda 2, there exists lambda prime 2, which factors through T double prime 2. There exists such a lambda prime 2, which is congruent to lambda 2 modulo pi, if and only if pi divides the relative congruence number. So this is the number which controls congruences between base changes and non-base changes. So if you want to draw a picture, you have the spectrum of T2, you have the spectrum of T1, you have the point lambda 1, you have the point lambda 2, and you are interested in points which are not base change, but still which are on this local, this is a local ring, okay? I localize. I could say they are local rings, okay, for me. Okay? And so I am interested in these points, and the existence of such a point is the non-triviality of the relative congruence number. While the congruences here come from the congruences here. If you have a congruence here, you have a congruence there by base change. Those are just coming from the congruences here. And so there should be a relation between the congruence number here, and so this is eta lambda 1. Here, this is eta lambda 2. And here, this part is eta lambda sharp. So, well, you hope that there is a factory, or maybe 1. So you hope there is a factorization of this type, and this is almost true. Okay. So what is true is that there is a divisibility, and the exact formula is true if you introduce some cohomological module. So now I introduce this cohomological module. Yeah, there is an L value which controls eta lambda sharp. This is the content of our work. You will see. That's exactly what we do. Yeah. So first of all, there are cases where this equality holds, but it's possible. But you need the rings, these Hecke algebras to be locally complete intersection. So if you are in the Taylor-Wiles situation, this is perfectly true. Okay? If not, there is a defect, but you can correct this defect by using modules, cohomology modules. So I need to state that. Takes time, but I'm sorry. So I consider now M2 T2 module, which is O flat, finite O flat. And so, I have decompositions. If you tensor by E, you can decompose as 1 T1 ME plus 1 T double prime 2 ME. And so, but ME is here, M2 is here. So we introduce as usual, but with this decomposition, we introduce something, maybe we call it M lower theta, M2, sorry. M2 lower theta, you can guess what it is. It is M2 intersection 1 T1, what 1 T1 is 1 theta actually. 1 theta of M2E. And we introduce M2 upper theta, which is 1 theta M2. And as usual, this is not contained in M2. Okay, be careful. This one, by definition, is contained in M2. And of course, we have this inclusion, M2 theta included into M2 theta. So what we do now is, so how can you characterize this module? This module is the largest sub on which T2 acts through T1 by theta. Okay, this is the largest sub on which T2 acts by T1 through theta. And this one is the largest quotient on which is, but it's, well, yeah, it's a, yeah, this one is a quotient of M2, okay, you see? You can, maybe, I don't know whether you want to, yeah, it is useful. What is the kernel? Well, the kernel will be something I should denote by M2 T double prime, which is M2 intersection 1 T double 2 ME. This is the kernel. You have an exact sequence like this. So it's a quotient of M2 by this submodule. Okay, so, so what you can do is you can, as I said, this is a module over the Hecke algebra T1. This is a module over the Hecke algebra T1. So what I do is I consider M2 theta and I apply lambda 1. So, of course, this is M2 lambda 2 because the composition of theta and lambda 1 is equal to lambda 2. But on the other hand, I can apply also lambda 1 to M2 theta. So I apply, so I denote it by this lambda 1. This is applying 1 lambda 1 to this T1 module. And so this is contained in here. This is rank 1. So this quotient is a finite monogeneous homodule, which I call the M2 relative congruence module. So the definition M2 lambda 2 over M2 theta lambda 1 is C lambda 1 sharp of M2, and it is isomorphic to O modulo something which we denote by eta lambda 1 sharp of M2. So that's the definition of the M2 relative congruence number. If you look carefully at the definition I gave for the Hecke relative congruence number, you will see that my definition says that eta lambda sharp of this module T2, this is a T2 module, T2 is a T2 module, this is what I defined as eta lambda sharp Hecke. Okay. If you take T2 itself, so if it is free, if M2 is free, the relative the T2 relative congruence number is relative congruence number. So now you have this definition, and the point is that, sorry? Yeah, I just write an exact sequence and I stop. Because that was the point of this introduction. So the exact sequence is the following. M2 lambda 2, sorry, lambda 2 divided by M2 lambda 2 goes to M2 lambda 2 divided by M2 theta lambda 1, and the kernel is something obvious, which is probably M2 theta lambda 1 divided by something which I write M2 theta lambda 1, which is this. This is that. But the consequence is that this, so the length of this module is eta lambda 2 of M2. And so it is the product of the length of this module. By definition, this is what I called eta lambda 1 sharp of M2 times the length of this module, which is eta lambda 1 of M2 theta. So this formula is always true. So in particular, if you take M2 to be T2, you get that eta lambda 2 is eta lambda 1, is eta lambda 1 sharp times, unfortunately, this thing which is not exactly the Hecke thing, it is the Hecke thing, it is something associated to a module, which is, if you like, T2 theta. And this is a T1 module which may not be free. And this is why you have a perfectly correct factorization, but this factorization is not exactly involving eta lambda 1 in general. In the case of a locally complete intersection ring, this is eta lambda 1. But, well, you have a factorization, but it's not exactly the one you would hope. A pity, but so this is what you hope, which is true for, which is true if the rings are locally complete intersection, which is rare. Usually you have T1, which is locally complete intersection, but not T2. So if both are LCI, you have this exact formula. If not, you have this exact formula, which implies a divisibility, but we will manage using only the divisibility. So you will have this divisibility. Okay, and that's the end of the formalism.
Thank you very much for this lecture. Are there questions or comments? If there are no questions, let's answer.